So let's do some Lewis structures here. And so we have Lewis structures for ionic compounds. For example, let's take a look at magnesium and oxygen. If I have magnesium and oxygen, are they going to share electrons, or is it going to be a winner-take-all scenario? Well, is it going to form a covalent bond, or is it going to form an ionic bond? Well, one rule that we had is that, remember the rule a long time ago, metals and nonmetals form ionic, right? And nonmetals form, that's because of the differences in electronegativity, but let's take a look at the electronegativity difference really quick. If we look at magnesium, go to the electronegativity chart here. What's the electronegativity of magnesium? It's a 1.3, and then oxygen is a 3.4. So 1.3, 3.4, the difference is 2.1. If the difference is 2.1, then we call it ionic. So this is winner take all. That means oxygen wants 2 electrons, and it's going to take them. It's not going to share. Metals have low electronegativities, nonmetals have high electronegativities. So typically metals and nonmetals are going to be ionic. And so we got an ionic bond. Well, that's going to form this ionic compound. So magnesium now has no valence electrons. We show that by whenever we have a charged species like this, we write square brackets around it. And then oxygen's now going to have an octet because it's just taking those. So it's winner take all. So this is the Lewis structure for magnesium oxide. Magnesium oxide. Now magnesium oxide forms a lattice, so this would just be one formula unit of that lattice. And the lattice of magnesium oxide just looks like the same as sodium chloride. Okay, now for covalent compounds, then it's going to be a bit different. Like say, for example, oxygen, what's going to be harder to oxidize than magnesium? Well, let's say oxygen and, let's go with oxygen and nitrogen, or oxygen and carbon. Well, we'll do carbon. We'll do oxygen and carbon. So oxygen wants how many electrons? It wants 2. Carbon has how many valence electrons? Four. It's in group 4, so that's 4 valent. So we draw the Lewis symbols like this. And so in this case, what kind of bond is this going to be? Well, carbon versus oxygen. Carbon is a 2.6. Oxygen is a 3.4. So the difference is 0.8. If the difference is 0.8, what type of bond is that? Polar covalent. So it should be a polar covalent bond. And so that means it's not winner take all. It's not going to form an ionic bond. It's going to form a polar covalent bond. And oxygen wants 2. So what's going to happen is it's going to gain this one and it's going to gain that one. And so what we're going to end up with is something that looks like this. Now this satisfies the octet rule for oxygen because we look at the total number of electrons surrounding it and we count it 2, 4, 6, 8. There are 8 electrons. But however, carbon is not there yet. And so what can happen is another oxygen can come in. Another oxygen comes in and tries to take the remaining 2 electrons on carbon. It's not going to completely strip them off because it's not strong enough. It doesn't have high enough electronegativity. And so what we end up with is something like this, which we call carbon dioxide. And so carbon dioxide can be written as having this. Each oxygen shares a pair of electrons rather than a single electron. So what we end up with is a double bond. It's called a double bond here. Double bond. Now, when we look at the octet rule is satisfied here. The octet rule just means we try to get 8 around atoms other than hydrogen. And so when we look at CO2, it satisfies the octet rule. The octet rule says, do I have 8 around this oxygen on the glide? Yes. Do I have 8 around carbon? Yes, if I double count. Do I have 8 around this oxygen? Yes, if I double count. And so if I look at each circle will have 8 electrons within it, which means each atom has an octet. And so this is called the octet rule. And the octet rule is important in Lewis structures, covalent. So what we end up with is polar covalent bonds. These are polar covalent bonds. However, CO2 is nonpolar because these two polar covalent bonds kind of equal and opposed, but each one of these is polar covalent. We'll talk about molecular polarity later. Okay, now these molecules can get quite complex. You know, this forms a molecule, a CO2 molecule. This forms a formula unit. We don't call this a molecule. This is a formula unit of the larger crystal lattice. And since these molecules can get quite complex, we don't draw molecule structures based on how I did it here. You know, how I did it here is kind of visually, this is what's happening. You know, oxygen's trying to take the electrons. When we draw Lewis structures for CO2, I follow a totally different procedure. And let's draw the Lewis structure for CO2 based on the procedure in chapter 13 here. And so we're going to just do that really quick. Should just take a couple of minutes. So I need to draw the Lewis structure for CO2 based on this procedure in chapter 13. So step 1, count the total number of valence electrons. So carbon has 4 valence electrons, oxygen has 6 valence electrons, and the second oxygen has 6 valence electrons. So altogether I have 4 plus 6 is 10, plus I have 16 valence electrons total. This is a total of 16 valence electrons. That's step 1. Step 2, place the least electronegative atom in the center. Oh, okay, adjust for charge. There's no charge here, so we don't have to worry about it. And so step 2 is I'm going to put the least electronegative. Well, least electronegative, what's carbon or oxygen? Which one wants electrons more, carbon or oxygen? Oxygen. So carbon goes in the center, and that means the oxygen are on the ends here. This is the tentative. Draw the tentative diagram, join atoms by single bonds. So that's what I did. Add unshared pairs to complete the octet around all atoms except hydrogen. So what I'm going to do is I'm going to draw pairs. First I want to do what we call the peripheral, not the central. And so first I want to complete the octet here. You see that's 2, 4, 6, 8. That's 8 electrons because the line counts as 2. 2, 4, 6, 8. And so I've completed the octet, both. And so if I look at this oxygen has 8 electrons surrounding it. That's good. This oxygen has 8 electrons surrounding it. Well, oxygen wants 8 electrons because it can fill its shell. Add unshared pairs to complete the octet around all atoms. Okay, now, do I have any other pairs? Well, how many electrons have I used so far? I've used 2, 4, 6, 8, 10, 12, 14, 16. I've used up 16 electrons. I have no more electrons. Does carbon have an octet? No, carbon does not have an octet. If I look at carbon, carbon's missing an octet. Carbon only has 2, 4. So carbon's less than an octet. Oxygen is at an octet. Calculate the number of valence electrons in tentative diagram and compare with actual. So I have 16 in the tentative diagram, I have 16 electrons actual. If the diagram has more, remove. Well, the diagram doesn't have more, so I don't have to remove. Repeat the number process until the number matches. Check the Lewis structure. Hydrogen atom must have only one pair. Step 6. Step 6 is missing. Step 6 is if I don't have an octet around the central carbon, what I'm going to do is I'm going to take a peripheral set and then bring it in to form a multiple bond. And so what I'm going to do is I'm going to take this set and bring it in here. That's not going to change the number around oxygen. It's still going to have 8 total, but now one additional pair is shared. And that's going to bump up carbon. But now carbon still doesn't have enough. Carbon's still missing 1 pair. It's got 2, 4, 6. So what I'm going to do is I'm going to do it one more time and share it. So what I end up with is this structure here, the same structure we had earlier. So what we're going to do is we're going to get practice with this procedure in generating the Lewis structure based on following these steps, plus some additional steps. Okay, I'll stop here.